Hi everybody. So yeah, I wanted to make a correction here on how I set up both classes exactly like this, and well, so I want to start off with where my mistake was, and it's a good one because it's a common student mistake as well. So look at me go. Yeah, I did this on purpose. I did this on purpose, you guys. Oh, and then I'm also going to say that this hanging mass, is going to be M1. So the mass of the wheel is just going to be MW. I'm not going to draw the spokes for simplicity's sake. The radius of the wheel is going to be capital R. And my original thing too, so, and if you see over here, here you go, you got the falling wheel, and then I got a hanging mass right here and everything like that. So in this case, I'm using the HEDH3, which has its own mass. So there it is, 854.4 grams, and then the hanging mass is 20 grams. And then I'm going to use this for something I'm going to explain later. So there's going to be parts to this video. And I just wanted to start off with what I did incorrectly. So I originally said, okay, well, so what you guys want to do is just make torque, because it's asking you, and I said it's asking you to graph, which I misread. They're not necessarily asking you to graph. Although I would try and make a habit of trying to make graphs and stuff, because you're going to see this a lot on the AP exam. So then I said, oh, do torque net equals I alpha, right? And then alpha is equal to, right, alpha is just, and then I said, alpha is equal to A over R, right? So I could just use this, right? The initial velocity here is 0. Let it drop, right? Let it drop until it hits the bottom. The displacement, delta y, you can measure the displacement, and then find out the time it takes, and then you could calculate the acceleration. And then with that acceleration, you can plug that in there, right? And then you could hang different masses. So hang another mass, hang another mass, hang another mass, and just keep doing the acceleration and that acceleration. And by hanging all the new masses, that's going to change your torque, right? Your net torque, which will change then, or which will allow you to, basically what I was getting at is, and even this is kind of wrong. I don't want to go into too much of why. If I graph this, boom, I was saying, oh, look at this, and the slope is going to be my moment of inertia, right? And then I could use that slope equaling that the moment of inertia they told me is beta mr squared, and then I can use that to calculate beta. That's one way to do it. I was wrong. Because if I add mass, if I keep changing mass, not only, because when you do an experiment, right, you only want to change one variable. So if I change this variable, I could then effectively change that variable. That was my intent. I'm changing this, thus changing the angular acceleration. However, if I change the mass here, I'm changing the whole mass of this entire system. So if I keep changing the mass, I'm also changing the inertia of the system, and that is not just bad science, that is super bad science. There's one thing between bad form and just bad science. So I would I would ignore this idea. So let me get into where this would be okay. So here's where this would be okay to do. Now let's draw out a free body diagram. So or a force diagram for, let's do similar to what we did in class. So for this wheel here, there would be a tension force being applied here, and yeah, so there's a tension force being applied here, and then if you're the hanging mass, that hasn't reached the ground yet, there's going to be also that same tension force. And then the weight, M1G, right? Pulling it down. Now, let's hold on to this. Let's just throw it down here really quickly. If you could measure the tension, so and then if I did this torque, there's only one torque acting here. So I would have the I would have my r vector. Here's my r vector like that, which happens to be exactly equal to the radius there. So if okay, and then this would be r, I'll call it rt. So rt, it would be rt. So where the r vector for where the tension force is being applied times the tension force itself times the angle between the tension force and that. So it's I alpha. So a couple things here. The angle here is going to be 90. So this is just going to be 1. And then RT this is happening on the outside of the pulley, which is just going to be, or the outside of the wheel, which is just the radius of the wheel itself. So it's R FT equals I alpha. And then alpha is A over R, right? So I would have been correct if you could measure the tension force outright. And in fact, there was an AP exam question last year where students were asked to, what would you measure and what would you need to graph, et cetera, in order to make a graph that you could find the moment of inertia of your disc or something like that, or the mass of the disc or something like that. And you could have said, I'm going to measure the tension, because you could, if I attached like instead of using this mass, if I just pulled down with like a spring scale or something like that, then I could measure the tension outright, and then I could totally use this, because if I pull down it with different forces, I haven't changed the moment of inertia, or I haven't changed the inertia of the system. So this would work if that was the case. Then I could graph, the radius would be the same. I could exert different tension forces. I could pull down at different forces, measure the acceleration that I get going down there, and then I could graph, graph those two things, and then get my moment of inertia as my slope. But that's not the case. So here's what I'm going to recommend instead. First off, they already say, I found out later, on the AP exam, they're probably going to require you to use a graph. Sometimes they might, and be careful with terms like this. So although this thing here says, use data table and graph to collect and analyze data if needed, meaning you don't necessarily need to do that. So, and then it says, follow the instructions below. So after all this graph stuff, it gives you all of this. Select one video from the data collection used to determine the rotational inertia of the bike wheel. So it just tells you to select one video. You don't have to go through all the different masses like I was saying, or things like that. And then it says we can express the rotational inertia. So then once you got the moment of inertia from the video, then find out what beta is using this equation here and this data here. All right, so if you want to try that now on your own, you're free to do that on your own, but I'm going to kind of just keep going here. So what I found this out from students who came into office hours. I found out about my mistake here from students who came into office hours, particularly Jaden. Thank you very much for bringing this up. And what Jaden was working with a partner, and what they decided to do is that they would to make, because I was telling them that I was requiring them to make a graph, and this is not a bad idea. So to make a graph, you could do this. So again, this starts at rest, so the initial velocity is 0. And then the displacement, the displacement is delta y. And I'm going to do something a little different from what he did. He did every centimeter that went down, he recorded the time. I'm going to do the opposite. If I watch this thing fall, oops, I didn't put my, well, let's look at the amount of time that it takes to fall. So it's taking about almost a little less than 2 seconds. So if I do about every 0.2, if I do like every 0.2 seconds and find out how far it fell, I could then get get enough data, maybe get like 8 data points or something like that, that I could then graph here and use the graph to get the acceleration. And that would be using a graph in order to do what I'm about to do. So again, if you want to try that, you're free to try that. But okay. So what I'm basically saying is every 0.2 seconds, measure out how high or how the displacement of this of this thing. So what I'm doing in this, what is this, yellow color, like that, right? It would keep getting. I would get more data points than this, but I would and I'd be able to get the time, right? So so the time is constant, and then I'm measuring how far away they are as they go down, and then I would graph, and then I could graph. Might as well just use this graph. I could graph then my displacement as a function of time. But if I did that, if I graphed my displacement as a function of time, you get a graph that does this. And that's not a linear line. That's not going to help me get a slope. That's just not, the slope is constantly changing. So you could do a couple things. You could look at that. Well, no, I'm not going to. Now, but I could look at this and go, wait a minute, I'm modeling this off of this kinematic equation. Let's just say V naught. V naught t plus 1/2 a t squared. And so my initial velocity is 0. And I'm basically saying that I'm modeling it off of this. So delta y equals 1/2 a times t squared. And the thing that I'm changing is the time. I'm controlling the time. I'm saying every 0.2 seconds that goes by, I'm measuring the position. And really, I should just say position here, where this is, so this is that. So where my initial position is going to be 0. That's what I'm identifying as 0. And I get this. So I'm saying that depending on the time, right, after every 0.2 seconds, I'm finding out what the position is. So if I graph that, and that means this is time squared. This, my independent variable is being squared. So this should be time squared. So if I graph this versus time squared, I would end up getting an actual line out of that. I would be able to get a line out of that. And the slope would be equal to this, 1/2 a. Again, if you want to try this on your own, do this on your own and see how far you can get in terms of trying to calculate the moment of inertia and trying to calculate the that beta right there. So slope is 1/2 a. So in order to get a, it's going to be equal to twice my slope. Right? So that would give me the acceleration. Now I'm going to go back into torque net equals I alpha, knowing I have A. I know A. I also, they told me the hanging mass, in this case, in the case that I used right here, it was a 20 gram mass. And I also know the mass of the pulley. It's right here. Or, I'm sorry, the mass of the wheel I got there. You can use a different trial if you wanted to. It doesn't matter. And then I could also get the radius of the wheel. Boom. You know, so I'm not gonna go into any of that. That'll be for you to do, to get the radius of the wheel and all that. But I wanted to show you that. But now and here's my issue again. So again, torque net equals I alpha. Well, the torque, there's only one torque here. That's what's nice here. It's just the tension force, right, from the tension force. So that's going to be the torque from the tension force equals I alpha. And I'm going to make all this. So this is going to be the positive direction. And then down is going to be the positive direction there. Again, whatever direction your acceleration points, just make that positive. So then using RF sine theta as the definition of any torque. So I'm going to plug that in there. So this is going to be RT FT sine theta t equals the moment of inertia multiplied by, let's go ahead and throw in as well, right? I know that alpha is the linear acceleration over r. And in this case, it's going to be capital R, because the linear acceleration is happening on the edge, on the edge of the disk there. So all of that I'll check out as being at the radius. So I could take that and plug that in there. So this is going to be A over R, just to get that in there. And then now I got, also this radius as well, RT. RT is also the radius of the disk. We talked about that already. I'm kind of copying right here what I did. So this is going to be R, FT, and then again, sine of theta t in this case is 90. Sine of 90 is 1. So this is going to be the moment of inertia times A over R. So let's see. I got R. I got A. I know those. I know R. And now I need to get FT. If I can get FT, I'll be able to calculate the moment of inertia. Where do I go to get FT? Again, if I was able to measure FT outright, this would be much easier. And this is what I thought was happening, and I was wrong. So we'd have to do like we did in class. Let's go to Newton's second law and use this as our system. So this is now our system here. Let's use Newton's second law and see what we get. So again, we had this. Your tension force was up here, Ft. mg points down. That's m1g. Careful, it's not the same as the mass of my pulley, or the mass of the wheel. So now using F net equals ma. That's going to be... so m1g minus the tension force equals m1a. So my tension force is equal to this. And now I can take this and plug it in for my tension force. Where is that going to get me? That'll leave me with R. And then instead of the tension force, it's m1g minus m1a equals I A over R. Again, I know my acceleration. So I'm going to multiply both sides by R. So it's going to be R squared over A, m1g minus m1a, and I can finally get my moment of inertia. So that would help me answer question 2, which you guys will do. And then lastly, question 3, I think that's right. Question 2, question 3. Question 2, yeah, that'll give me the moment of inertia. For question 3, I'll just leave you with, they give you this equation. Remember, this is the mass of the wheel, so now that you got I, you should be able to find out what beta is. And to check to see if you're right, beta should be a number between 0 and 1. All right, so I hope that helps. Well, not just that it helps, I hope I've clarified things a little bit. Again, this particular problem is saying you do not have to use a graph. You could have used like my old method of just like letting it drop to the bottom and calculating A outright. But just for practice on an AP exam, you want to try and get used to graphing something because that's a common thing. And there's all sorts of reasons I want to go into of why it's better to graph things, and I have in the past, and I'm going to shut up right now so this video doesn't go on any longer than it has. So there you go. Hope that helps. All right. Thank you guys. Bye.